Today we're going to learn how to the definition of stoichiometry. So let's look at that word. It's a funny looking word. Stoichiometry. Stoichiometry is a study of quantitative. What does the word quantitative mean before we move on? What is quantitative? If I'm looking at quantitative numbers. So I'm going to do a quantitative analysis between the relationship of products and reactants. Reactants and products, where have I heard that word before? In a chemical equation, right? So we're going to do a little conversion. We're going to look at quantitative analysis. Up here I have the equation for photosynthesis. And I already balanced it for you. And we want to balance it because what law are we trying to follow? Conservation. Yes, we are. So stoichiometry does this. It is a quantitative analysis, and it follows the law of conservation of mass, LOCOM. That's what it does. That's what we want it to do. Okay, so what does this mean? Well, first of all, I really have to understand the relationships here. I know on the left-hand side of the reaction, those are the reactants. Very good. These are the reactants, and they yield the products. Good. So what does that mean? Well, we have to use those numbers. Before it used to be like if I had 6 atoms of carbon dioxide plus 6 molecules of carbon dioxide plus 6 molecules of water, I would get 1 molecule of glucose plus 6 diatomic molecules of oxygen. Yes? That's what it says. However, what does that mean? Well, I'm going to look at some relationships here. All right? The relationships are like this. Instead of using particular molecules or atoms, I'm going to use the quantity of moles. All right? Moles. This means that, would you believe, 6 moles of carbon dioxide react with 6 moles of water. Yes? Okay. Would you believe 6 moles of water react with 6 moles of carbon dioxide? Would you believe, what am I actually doing here? What, have you ever seen these kind of relationships before? Have you ever seen this in a fraction form before? What do we call those? We use them conversions. We're going to be looking at these conversions. So I'm writing down all the conversions that they have here. It's kind of interesting if I would write them all, and it's going to take me a while. So please bear with me. If you want to write them down with me, that's great. I write one and then the other. So 6 moles of water produce 1 mole of glucose, and 1 mole of glucose results from 6 moles of water. Where else am I at? I've done that. How many do I have for so far? 6. I should end up with 12 when I'm done. Can you help me think of the other 12 or the other 6? What other relationships do I have? I've had these 2 and those 2 and these 2. What else do I have to have a relationship with? Six moles carbon dioxide, 6 moles of oxygen, 6 moles of oxygen, 6 moles of carbon dioxide, 6 moles of water, 6 moles of oxygen, 6 moles of oxygen, 6 moles of water. Okay, I said there's 12. I have 3, 6, 9. I have 10. What other two things have I not combined yet? The two products, good. 1 mole of glucose, 6 mole of oxygen, 6 mole of oxygen, 1 mole of. Okay, those are all the conversion factors that we have for this equation. So how is it going to help us? Well, if you think about it, it's going to help us tell us if I started with, okay, you can look at this, right? If I started with 12 moles of carbon dioxide, 12 moles of carbon dioxide, potentially, how many moles of glucose would I get? If I started with 12 of this, potentially, how many moles of this would I get? Okay, it's a 6-to-1 right now. If I went 12 to 2. What if I was at 3 moles of carbon dioxide? How many moles of glucose would I get? Half. Very good. So I'm going to be using this, but it's not going to always be so simple, is it? The reason I do this is because I want to make sure that I'm going to follow the law of conservation of mass. This always helps me. These conversion factors will help me get from how many reactants are going to react to how many products. I need to know these. And where do these all come from? How did I see all these ratios? Where do they come from? They kept paying for the equation. So these are very important. These are conversion factors from balanced. Why do you think I capitalized balanced? What's going to happen to some of us? Think we might forget how to balance it? So remember, these are the conversion factors from balanced equations. You got it all down? No. Okay, I'm going to give a minute here. We're going to write it down, and then we're going to utilize it a little bit. All right? So we have our balanced equation, reactants yielding products. We're going to use stoichiometry, which is the quantitative analysis of chemical reactions, and it always follows the law of conservation of mass. However, I'm going to be working in industry. I'm going to be working in industry as a chemist in industry. And let's say I am a paint chemist, right? And I have to get different things from different places and whatnot. Why would it be important for me to know about stoichiometry? I'm making paints. I have to order stuff from other companies. Why would it be important for me to know stoichiometry? That's an essential question. That's an important question. I want you to think about that. Think about these two statements up here. It's a quantitative analysis, and it follows the law of conservation of mass. Anybody have any ideas? Do you want a different scenario?
Can you explain the definition of stoichiometry?
Stoichiometry is the quantitative analysis. Okay, you're doing a number analysis, number thing, between the reactants and products of a chemical reaction.
Well, if you're trying to get a certain color of paint, you would have to know that. The number of reactants, I don't know.
Yeah, if you're making something, you need to know how much of each you need.
Yeah.
What if I don't buy enough?
Then
What if I buy too much? Is the company going to be happy with me? No. You could. However, if they only have a shelf life of so long, storage may not be the answer. I also look at this, and you might, as every one of you, whoever does the cooking in your house and has to buy the groceries, follows stoichiometry. Why do I say that?
For your ingredients.
Figure out your ingredients. Okay? If I know what I need to make something, okay? If I know if there's a birthday coming up and I want to make a cake for one of my people in my home, I need to know I have to have eggs and oil and water in the cake mix, right? and stuff to make a frosting. If I don't have all that, I can't keep running to the store. Doesn't work that way. So we need to keep that in mind. Okay, does everybody have this down that wants it down?
No. I'll just take pictures though.
Okay, we have, yeah, pictures are good. My handwriting is bad. We good now? Okay, if you you can use your phone. These are pretty. We're not going to go into really complex or equations today or quantitative analysis today. So if you can use your phone, it won't be a problem to do your as a calculator. That won't be a problem. Okay, you have that list. I'm not giving you a new equation or anything. You have this list of factor conversions. All right. Let's suppose you have, I want to know, 0.178 moles of water. And you want to figure out how many moles of glucose you're going to get. So you always start with what you know you have. I have 0.178 moles of water. Using conversion factors, we have to eventually get to what? Moles of glucose. Now, from our previous study of moles, if I have moles of water up here, what's my label down here? Moles of water. Whatever in your numerator as your label must be in your denominator. All right, is there a relationship between moles of water and moles of glucose? Yes or no? Yes. How many moles of water make how many moles of glucose? 6 moles make 1 mole of glucose. Is this one of the conversion factors that you wrote down? Yes, it is. Why is it written this way? My numerator is moles of water. My denominator is moles of water. I want to go to glucose. There's your relationship. So now what do I do to solve this problem?
You could divide it by 6.
I take 0.178 times 1 divided by 6, and I magically get
0.0296.
0.0296 moles. Now, that is a totally correct answer, I think. All right. Why did you stop here? Because I'm sure it isn't what it is. This what the answer was?
No, it's 0.029666.
Okay, 2966666. So maybe this should be a 7.
Yeah.
All right. Why did you stop there?
Because I didn't want it to be too long.
Okay, you didn't want it to be too long. What do we call that when you don't want it to be too long because of this? Very good. Significant digits. We had to follow. We have 3 significant digits here. So our answer must have 3 significant digits there. Yes or no? Recall that? Okay, let's try another one. Suppose you have, oh, I don't know, 1.83 moles of carbon dioxide, and you want to find out how many moles of oxygen it is. Now, some of you can visually see that and go, yeah, I know what that answer is, because they're the same, correct? Can you see that? If you can't, let's go through it anyway. So I start again. I have 1.83 moles of carbon dioxide. What label goes down here? Moles of carbon dioxide. Does it have a relationship to moles of oxygen? Mm-hmm. Because it's in the same balanced equation. And I know that for the balanced equation, this is a 6 and this is a 6. Yes? So that's really 1, isn't it? So my answer is still 1. But it just is nice practice. Again, when you solve these problems, You want to use those conversion factors, and it has to be from a balanced equation. This is very, very important. Muy importante. Yes? See? All right. So with that, after this, you should be able to do that first book assignment and maybe start on the second one. Right? On Thursday, our next lecture will be on how to go from grams. How about if they give me grams of substance? All right. Any questions? Okay, thank you.